Welcome everyone. In this lesson we're going to be looking at the differentiation technique called implicit differentiation. And so before we kind of get into that, we're going to first look at what we call implicitly defined functions. So this is going to be actually what we're differentiating. And then once we learn the technique, we're going to do some of the usual things that we use derivatives for. So slope of the tangent line, equation of the tangent line, and so on. All right, so first, what is an implicitly defined function? And we're going to start by considering kind of what we're used to, and that's explicitly defined functions. All right, so every function we've used in the course so far probably has fit into this category. And for our discussion here, we're going to be looking at two variable equations. So equations involving two variables, and usually, well, at least for our discussion here, x's and y's. All right, so we're going to talk a little bit about an explicitly defined function. And so here, variable y is going to be explicitly written as a function of x. So what do we mean by that? Well, here's a graph of what an explicitly defined function might look like. And turns out, as a little example, this is the function y equal to x squared minus 1. And so when we look at this, we have an equation involving two variables. So there's two variables here, x's and y's. But the way this is written, it's written in the form y equals. So y here is written as a function of x. Y is equal to this function of x. And it's explicit. We're actually saying here, in this equation, y is equal to this function of x. So we're actually explicitly writing this down. So y equals is explicitly stated here in our equation. We're saying what y is actually equal to here, and it's equal to this function of x. All right, so that's an explicit function. What do we mean by an implicitly defined function? Well, just the opposite. So let's consider this example. This is the equation x squared plus y squared equal to 4. So this is a circle of radius 2. And here we have an equation involving two variables, x's and y's. But now this one is not in the form y equals. So it's the x's and y's are kind of all mixed together here on the left side. We haven't actually solved for y. Maybe we could. So for this equation, we actually could do some solving for y. That's not always the case, though. But it's this equation, and the x's and y's are sort of mixed together. But it still makes sense to think of y as a function of x. We just haven't finished, in essence, solving for y. So y is going to be just implicitly defined as a function of variable x. So we're going to be looking at equations involving two variables, x's and y's. If we have an equation like this, y equals, and then all x terms on the right, this is just a regular explicit function. We have all of our differentiation techniques that tell us what to do. If we have an equation like this, x squared plus y squared equal to 4, we haven't actually solved for y yet. So this is, we're viewing y as, we're still going to view y as a function of x, but now we don't actually know what that formula is. We don't have a formula for what that function is. So we're viewing y as an implicit function of x. So we don't have the actual formula written down. We have this equation that we could potentially use to solve for that formula. But in both of these cases, we can still graph the curve in both of these cases, And it still makes sense to talk about things like the tangent line. So we still want to talk about, in both of these cases, things like the derivative dy dx, which is giving us the slope of the tangent line. So for this, just our regular functions, explicit functions, dy dx tells us the slope of the tangent line. For implicitly defined functions, we can still calculate dy dx, and it's still going to give us the slope of the tangent line. Now, one thing to kind of just be careful of with these implicitly defined functions is the equation sometimes gives you more points. There's more points on this curve than there actually could be for a function. So one thing to keep in mind is the vertical line test. So an explicitly defined function is going to pass the vertical line test. And for this curve x squared plus y squared equal to 4, for y to actually be a function, we only consider part of the curve. So sometimes this happens where we can only consider part of the curve. And so normally we're interested in a particular point. So we just consider kind of a portion of the curve around that point. So it's still going to pass, but only if we consider just a portion of the curve. All right, so we're going to see some examples of this. So let's start by talking about the implicit differentiation technique. So we're going to be considering an equation with two variables, and our two variables are going to be x and y, at least for the beginning, but this could be done with other variables. And how we're going to do this is we're going to view x as a variable. And we're going to, well, we're going to view y as a variable too. So we're going to view both of these as variables. The difference is we're also going to view y as a function. So when we have an equation involving two variables, we're going to treat x like a variable, only a variable. We're also going to treat y like a variable, so it's a perfectly good variable on its own. But then we're also kind of building into it, we're thinking of y as an implicit function of x. So we're kind of thinking anytime we're going to see a y in an equation, we're going to think of it both as a variable and also as a function of x. So as a little example here, just to kind of make this concrete, let's consider the equation x squared plus y cubed plus xy equal to 3. So here we have an equation. All the x's and y's are kind of all mixed together here. When we look at this equation, we're going to think of any x that we see as just as a variable. And we're going to think of the y's that we see here both as variables, but then also as kind of being a function of x. So almost think of it as like there's some hidden x terms hidden inside of this y. So as a little example, let's consider the case of this function f of x equal to x to the fourth plus 3 all cubed. How would we differentiate this? Well, this is going to involve chain rule. So how would the derivative look? Well, this is a power function, so we'd start by differentiating the outer function. So 3, bring the 3 down, keep our inner function the same, subtract 1 from the exponent, and then we take the term that's inside and multiply by its derivative. So we take that x to the fourth plus 3, and then we just multiply by its derivative. So this is what chain rule says. And so if we're viewing y as both a variable and a function, we're going to see kind of something interesting when we try to differentiate a y term. So let's get into how implicit differentiation is going to work. So let's look at this equation, and when we see a term only involving x, how do we differentiate it? So we have this term only involving an x, this x squared right here. So just that x squared term, there's only an x there. How are we going to differentiate this? Well, we just differentiate it like usual. So we know how to do the derivative of x squared. It'll be just 2x. All right, so we have this equation. We're viewing x as a variable, we're viewing y as a variable, but we're also viewing y as a function of x. So we're going through each of these terms, and when we only see an x, we differentiate it like usual. Now, if we have a term involving only a y, so that's like the y cubed term that we see in our equation. So that y cubed, there's only a y there. This term has both an x and a y. This term doesn't have a y. How are we going to differentiate this y term? Well, it's kind of a two-step process here. We're going to differentiate it like usual. And then, once we've done that, we're going to multiply the result by y prime. So why are we doing that? Well, we're viewing y kind of as two things. We're viewing it as a variable. So that's why we're going to differentiate it like usual. But then we're also viewing y as a function of x. So chain rule is actually going to apply. We want to multiply by y prime. That's the second part, is because really we're viewing y here as a function of x. So we're going to use chain rule. We're treating it as a function, so we have to do this additional step. So if we kind of go back to this chain rule case, if we had this kind of explicit function, f of x, which was this composition, x to the fourth plus 3 raised to the third, what would we do? We differentiate the outer part and then multiply by the derivative of the inner part. Now, if we just had y cubed, we're going to treat y cubed, we're really viewing this as a composition. We just don't have a formula yet for what y is. But the process is still going to be very similar. So the way we differentiate this, so if we wanted to differentiate y cubed, how is this going to work if we're viewing y as an implicit function of x? Well, we're going to differentiate the variable part, so do power rule, 3y squared. But then we're going to multiply by the derivative of y. So we're going to multiply by y prime. Just for the same reason that here we had this function, and f of x was x to the fourth plus 3 raised to the cubed, and that inner function was an explicit function. There was x's in there, and it's explicitly written. So we did chain rule. Here, we're viewing y cubed. There's x terms kind of hidden inside this y. So we're viewing y as a function of x. So we differentiate the outer function just like we normally would, so power rule in this case. But then we have to multiply by the derivative of the inner function. Now, the only thing kind of tricky here is we don't actually know what the formula is for the function is for y. So we're just multiplying by y prime. All right, we'll try this out in a few examples. But what happens if you have a term involving both x and y? What do we do then? Well, here we're viewing x as a variable, and we're viewing y as both a variable and a function. So really, again, there's these hidden x terms inside the y. So if we have an x times y, really this is like a product of two functions of x. So, if we see like an x times y, we might have to use product rule. So it depends on what you see. If you have an x divided by y or something like that, then you might have to use quotient rule. So it just depends on, what that other term is. So if you have a term involving both x's and y's, you might have to use some of our bigger rules, product rule, quotient rule, or maybe you have something a little bit more complicated. So maybe you have something like x plus 2y cubed. So there's x's and y's inside an outer function. You'd have to use chain rule. So it all depends on what's going on with your function. But if you have a term that's involving both an x and a y, you might have to use some of our bigger rules in order to differentiate it. All right, so let's try this out. So in the next video, we're going to see an example of how this actually works in practice. So we'll see you there.